So finding inverse transforms where there may have been a shift in the original function may prove to be a little bit more difficult, but until you find out where to look, and remember, the most important part of a Laplace transform is the denominator. The denominator tells you what function you started with. So that's where we're going to focus all of our efforts here. So with this one, it is very apparent that an s was replaced with an s plus 5. So that means that my function will be multiplied by e to the negative 5t times something. So to figure out the something, what we're going to do with the transform is bring it back to just plain old s. So we're going to deal with 2 over s to the 4th. Now what does that correspond to? Well, we know that the Laplace transform of t to the 3rd is 3 factorial over s to the 4th. Again, pay attention to the denominator. S to the 4th in the denominator meant t to the 3rd as the original function. So if I want 2 times s to the 4th, so 2 over s to the 4th is equal to, well, I'm going to have to multiply by 3 factorial over 3 factorial. And I'm just going to do a little bit of rearranging. This is 2 over 3 factorial times 3 factorial over s to the 4th. This part here is 1/3 because 3 factorial is 6. This corresponds back to t to the 3rd. So that means that it was 1/3 t to the 3rd. So that means that my function is e to the negative 5t times 1/3 times t to the 3rd, or 1/3 e to the negative 5t t to the 3rd. And there's our first inverse transform. Okay, at least with shifting. So let's take a look at another one just to get the hang of this. Now this one, again, denominator tells the tale, right? This is not looking like anything that we have done before. In fact, the denominator doesn't even factor. So the next strategy tells me maybe I should complete the square. So I'm going to rewrite s squared plus 4s plus 5 is equal to s squared plus 4s. Now, we're kind of familiar enough with certain coefficients that we know that the number that's going to complete the square here is 4. So I'm going to break up the 5 as 4 plus 1. And that means we have s plus 2, the quantity squared, plus 1. So that means my transform is equal to 3 over s plus 2 squared plus 1. Now, what's apparent here? I'm looking right at this and I'm saying, okay, my original function, which I'm just going to write a space for it here, must have had an e to the negative 2t in it because it looks like there is an s plus 2 where an s used to be. So we're going to find the inverse transform of 3 over s squared plus 1. Now, luckily, that one is very recognizable. We know that sine of t has transformed 1 over s squared plus 1. So this is 3 times the sine of t. So what does that mean? It means that my g of t is e to the negative 2t. I'm going to put this in a different color so you see where it comes from, times 3 times sine of t. Okay, and that's our original function. All right, one more. This one might be a little bit more difficult. So here again, denominator tells the story, right? And looking at that, it doesn't factor, so that means I'm not going to try partial fractions, but it does look like something that could be completing the square. So s squared plus 2s plus 17. Well, I know the number used to complete the square with a 2s is 1. So I'm going to break this up as s squared plus 2s plus 1 plus 16. And that means s squared, whoops, not s squared, means s plus 1 squared plus 16. That looks like a shifted denominator with a sum of squares. So I'm thinking sine or cosine probably. This is 2s over s plus 1 squared plus 16. Now, here's the problem. This is telling me that my original function, and again, I'm going to write it here. Well, I'll write it somewhere. I'm not going to write it right there, though. That means that my original function probably had an e to the negative t in it. So the goal is to figure out what is the rest of it. Well, here's the problem. there's not only an s plus 1 in the denominator, but if I'm going to replace s plus 1 with s, I got to worry about the numerator as well. This guy needs to be rewritten as well. So how do we handle that? Well, here's what we do. We say that this is 2 times, I need an s plus 1 to replace with s, and then minus 1, all over s plus 1 squared plus 16. So that means this and this are getting replaced with s because we already have the shift accounted for. So this is 2s minus 1 over s squared plus 16. So what does that correspond to? Well, I'm going to break up the function so that we can look at these separately, because we know that s over a sum of squares is a cosine, and we know that a constant over a sum of squares is a sine. So remember that cosine of at transforms to s over s squared plus a squared. So that means this is 2 cosine 4t. And we know that a over s squared plus a squared transforms to sine t, which means I'm going to need to multiply by 4 and 1/4 to make that work, because I know that this is the transform of sine of 4t. So that means this is minus 1/4 sine of 4t. And there we have it. So the original function, which I have here as h of t, is e to the negative t, already accounted for the shift, so that's why we took it out, times the quantity 2 cosine 4t minus 1/4 sine 4t. And there we have it, inverse transforms with shifts. These can be a bit more difficult, so give yourself a little bit of time to let this gel, because it really takes a while to get into the groove of it. But once you have it, you'll remember it for life. I guarantee it. Thanks a lot.